Chronostasis is a type of temporal illusion in which the first impression following the introduction of a new event or task demand to the brain appears to be extended in time. For example, chronostasis temporarily occurs when fixating on a target stimulus, immediately following a saccade, that is, quick eye movement. This elicits an overestimation in the temporal duration for which that target stimulus, that is, post-saccadic stimulus, was perceived. This effect can extend apparent durations by up to 500 ms, and is consistent with the idea that the visual system models events prior to perception. The best-known version of this illusion is known as the stopped clock illusion, wherein a subject's first impression of the second-hand movement of an analog clock, subsequent to one's directed attention, that is saccade, to the clock, is the perception of a slower than normal second-hand movement rate. When first observing the second hand, it appears to remain stationary for longer than the subsequent periods between movements. This illusion can also occur in the auditory and tactile domain. For instance, a study suggests that when someone listens to a ringing tone through telephone, while repetitively switching the receiver from one ear to the other, it causes the caller to overestimate the temporal duration between rings. Overall, chronostasis occurs as a result of a disconnection in the communication between visual sensation and perception. Sensation, information collected from our eyes, is usually directly interpreted to create our perception. This perception is the collection of information that we consciously interpret from visual information. However, quick eye movements known as saccades disrupt this flow of information. Because research into the neurology associated with visual processing is ongoing, there is renewed debate regarding the exact timing of changes in perception that lead to chronostasis. However, below is a description of the general series of events that lead to chronostasis, using the example of a student looking up from his desk toward a clock in the classroom. 1. The eyes receive information from the environment regarding one particular focus. This sensory input is sent directly to the visual cortex to be processed. After visual processing, we consciously perceive this object of focus. In the context of a student in a classroom, the student's eyes focus on a paper on their desk. After his eyes collect light reflected off of the paper and this information is processed in his visual cortex, the student consciously perceives the paper in front of him. 2. Following either a conscious decision or an involuntary perception of a stimulus in the periphery of the visual field, the eyes intend to move to a second target of interest. For the student described above, this may occur as he decides that he wishes to check the clock at the front of the classroom. 3. The muscles of the eye contract and it begins to quickly move towards the second object of interest through an action known as a saccade. As soon as this saccade begins, a signal is sent from the eye back to the brain. This signal, known as an efferent cortical trigger or efference copy, communicates to the brain that a saccade is about to begin. During saccades, the sensitivity of visual information collected by the eyes is greatly reduced and, thus, any image collected during this saccade is very blurry. In order to prevent the visual cortex from processing blurred sensory information, visual information collected by the eyes during a saccade is suppressed through a process known as saccadic masking. This is also the same mechanism used to prevent the experience of motion blur. 4. Following the completion of the saccade, the eyes now focus on the second object of interest. As soon as the saccade concludes, another efferent cortical trigger is sent from the eyes back to the brain. This signal communicates to the brain that the saccade has concluded. Prompted by this signal, the visual cortex once again resumes processing visual information. For the student, his eyes have now reached the clock and his brain's visual cortex begins to process information from his eyes. However, this second efferent trigger also communicates to the brain that a period of time has been missing from perception. To fill this gap in perception, visual information is processed in a manner known as neural antedating or backdating. In this visual processing, the gap in perception is filled in with information gathered after the saccade. For the student, The gap of time that occurred during the saccade is substituted with the processed image of the clock. Thus, immediately following the saccade, the second hand of the clock appears to stop in place before moving. In studying chronostasis and its underlying causes, there is potential bias in the experimental setting. In many experiments, participants are asked to perform some sort of task corresponding to sensory stimuli. This could cause the participants to anticipate stimuli, thus leading to bias. Also, many mechanisms involved in chronostasis are complex and difficult to measure. It is difficult for experimenters to observe the perceptive experiences of participants without being inside their mind. Furthermore, experimenters normally do not have access to the neural circuitry and neurotransmitters located inside the brain cases of their subjects.